My name is Carlos Villa from the National Magnet Lab. I'm going to start with, let me see if I remember how to hit all the right buttons in the right order. So if I do this, are we up?
Yep.
Fantastic. So yes, I'm the director of K-12 education programs. I got to add something, a new byline to my signature. I don't know if Jen knows yet, but I was the finalist for Florida State University Employee of the Year.
Oh, congratulations.
Wow, that's awesome.
I was in the top 3, and they email you and tell you, hey, you didn't win, but you made top 3. So I'm like, okay, I'll take it. So
were there more than 3 people?
Yes, they said there were about, they said over 20, so I'm guessing 21.
Oh, that's amazing. That's fantastic. Congratulations.
Yes.
It was. They sent me the letters that my boss had written and a few other people had written. It was very nice. But that's not why you're here. You're here to talk about what makes science. So I like having this argument about what makes science. There used to be a colleague at work that we used to argue about what the scientific method is. So it all ties in together. But briefly, are either of you familiar with the Magnet Lab? Yes, no, yes, excellent. I'm going to review just in case. We're one of 7 high magnetic field labs in the entire world. We're the only ones on the Western Hemisphere. But of the 7, we are the largest and we are the highest powered. So we do have most of the world's strongest magnets, which is a very cool thing to say. We are a user laboratory, and that means that our #1 job is to operate magnets for scientists to come in and use and do research with. We had over 2,000 user visits in 2019. I imagine 2020 is going to be a lower number, but still lots of scientists are still coming out to the lab using the facilities. And a cool thing that I didn't know, but we are using a lot more, some scientists send us the samples, we put the samples into the magnet, and then they can operate the magnets from their home computers. So we're able to do that if they're able to get the samples to us. Our operating budget for the last year was about $58 million, and most of that went to electricity. But we are funded by the National Science Foundation and the state of Florida, which means that the research is free to scientists on the condition that they share the research. We're here to broaden science understanding and appreciation. So we want scientists to share everything that they learn. Big surprise, the biggest misconception I get is that everything we do is about magnets, and it really isn't. Material science is actually the #1 topic that we research, followed by physics and engineering. We do chemistry, biology, biomedical, geochemistry, we've done pharmaceutical, oceanography, geochem I mentioned. We've even done some paleontology, which is very cool. So we do a little bit of everything. Our department, the Center for Integrating Research and Learning, we're the educational hub for the magnet. So we do the K-12 education outreach. We get about 5,000 students that we visit annually, and most of that is through field trips to the Magnet Lab, which of course we're not doing right now. But we also offer professional development, like what we're doing right now, workshops, conferences, and we now have virtual classroom outreach. So if you go to our website, you can request to have me come to your class just like this to do an activity with your kids. So the importance of scientific literacy. I have always been a fan of science. I remember being a kid and carrying the dinosaur dictionary around with me everywhere until the spine on that poor book broke. I bought my daughter the newest dinosaur dictionary and she carries it around everywhere. So what is the triumph of science? It's going from this to this. I mean, that's just cool in its own. You tell kids that this is what a cell phone used to look like, they don't believe you, they just don't. It means that car phones used to actually have a rotary dial, and then they looked like this in the higher end Porsches and Ferraris. And now we have this, of course, because everybody's got a phone and they carry it with them in the car. It means going from this, which would be an awesome room in my house I would love to play with. My kids would love to hit all those switches and fidget with all the knobs and everything. But this is what the first computer looked like. And now, of course, we've got this, the newest model, which has 2 screens on it, one of which is an interactive touchscreen. And I'm like, I want this. I need this in my life. But it also means going from this, which I remember playing, and football looking like this, to what's coming out next month, which is this. And that's not a photograph from a football game. That's from the video game. It's just ridiculous how how intelligent and how fast processing these devices are. So the turn of the science has gone from making our lives better, and of course, almost everything I mentioned is technology, but you can do the same with pharmaceuticals, with communication. Our ability to use Zoom now to sit down and have this web workshop and attend many more without having to leave our homes. I mean, it's just amazing what science does for us. I can't count books any faster, but it can do a lot of other stuff. Cancer chemical found in coffee. Now, here's where science literacy is important. We all appreciate science. Our kids all love what science gives them, but this is where you want them to make sure that we all are scientifically literate. Article in the newspaper, cancer chemical found in coffee. TV broadcast runs with that say, a new chemical in your coffee may be giving you cancer. Details at 11. Well, I'm gonna drink my coffee anyways because shortly thereafter, coffee prevents cancer. Oh, okay, so which one is it? Is it one? Is it both? Is it neither? It's probably a little bit of both. It's a blurry line where a chemical, and here it says it's called acrylamide, which happens to be in coffee, could be connected to cancer, and another chemical may be connected to preventing some sorts of breast cancer. So they're not saying drinking coffee is going to give you cancer or drinking coffee is going to prevent cancer, but they like to give you those wow headlines. And unfortunately, a lot of people go on Facebook, they see the headline, they share the article, and they don't bother reading to find out that it's a chemical that may or may not actually be in that coffee or may not actually be explicitly connected to cancer or to coffee. It happens here too. Housework cuts breast cancer risk. Well, you read that article, tell everybody you got to do more housework. It cuts your breast cancer risk. I'm pretty sure a man wrote this article. I bet money it was. But then there's also this one. Red wine antioxidant fights cancer. So this is how somebody can read a scientific journal, find the headline, make a connection, sell the article, and everybody's reading it and sharing it. Everybody's going to buy red wine, say, I'm buying red wine, it's going to fight cancer. That's not really how it works, but that's how we get to where we are because we don't really read the articles. We get caught by the headline. It's easy to click, share on Facebook, and then everyone else gets to see it. And if it's catchy enough, it goes viral. Here's why it's so important that we are scientifically literate. Are either of you familiar with the dihydrogen monoxide problem? And then I'm asking you too. Excellent. So there's this little article, a little activity that you can do with your children about a chemical called dihydrogen monoxide, which is actually also called hydrogen hydroxide, or you can also be called hydric acid. By naming rules in science, it fits into either one of those three. So you have this material called dihydrogen monoxide. I'm just going to tell you some of the facts about dihydrogen monoxide, starting with the fact that it is odorless and colorless. Inhalation can lead to death. Okay, well, that's a big wow right there. Okay, it's a major component of acid rain. It can cause severe burns. It can actually, I'm not going to say that. I'll say that for later. It's heavily used in nuclear power plants. In fact, I've even seen it used in coal power plants as well. Athletes have used it as a performance enhancer by putting it into their bodies. And it's also something that's also used in pesticides and herbicides too. And also dihydrogen monoxide is a carrier of pollution. So you list off all these things about dihydrogen monoxide. You ask your students, hey, what do you guys feel about this dihydrogen monoxide chemical? And hopefully they get on this page and they're like, bad, let's get rid of it, it's terrible. This is a real website that someone has organized, ban dihydrogen monoxide. If you look at it, there's flyers that you can download on that page that say overconsumption of DHMO can cause excessive sweating, urination, nausea, vomiting, and even death. That's true. Long-term exposure to solid dihydrogen monoxide can cause severe tissue damage. That is also true. DHMO is a primary ingredient in herbicides and pesticides. I mentioned that before. Leading cause of death by drowning. That is 100% true. And 100% of people that are exposed to DHMO are going to die. These are all facts. Now, let's let's get into the nuances of the science for a second, because dihydrogen monoxide is not what it appears to be, which is exactly what I wanted to do. Dihydrogen, di, the prefix, means two or twice or double. So dihydrogen means two hydrogen. Monoxide, if you think of Mr. Peanut with the monocle, one lens, one oxygen, monoxide. So mono means one, oxygen means one, monoxide. You put those two facts together, you've got H2 and O. Dihydrogen monoxide is another name for water. Now, none of the things I told you were a lie, all right? Overconsumption of DHMO can cause excessive sweating, urination, you drink a lot, you gotta go a lot, nausea, vomiting, and if you drink too much water and don't relieve yourself, it can cause your cells to burst and you can die from that. That's a fact. Long-term exposure to solid dihydrogen monoxide, better known as ice, can cause severe tissue damage. That is true, we call it frostbite. DHMO is a primary ingredient in herbicides and pesticides, and in cooking spaghetti and lasagna and a lot of my favorite foods, but it's an ingredient in herbicides and pesticides, that is true. DHMO is the leading cause of death by drowning. Yeah, every drowning case is done in water. Otherwise, there's a different reason for it, asphyxiation if you don't get enough oxygen in the air. So that's true. And 100% of people with exposure to DHMO will die. Well, 100% of people are going to die anyways. So that's a stretch on the truth, but it is still a fact, okay? I twisted the truth just a little bit to get you to buy into my fear-mongering, my, oh my God, DHMO is this dangerous chemical and it's gonna hurt and kill a lot of people, because I played on your lack of knowledge of the chemistry of the hydrogen monoxide. So that's my short rant on the importance of scientific literacy. Let's talk about what science is, all right? And we start by doing this, like what is science? Well, scientific knowledge is durable, okay? It's something that can be tested, it can be proven, it can be relied on. Scientific ideas are tentative. We have the ability, and you have seen it during the COVID-19 crisis, to do further research and adjust our beliefs on what is happening. I remember one of the very first things we said, well, masks aren't going to do anything because they're not all N95 masks. And we realized, wait, hold on, it does work to some extent. They're not perfect, but they work better than no mask. So we told everybody, okay, use a mask and socially distance. And I know a lot of people got upset and saying, well, scientists keep changing their mind. I'm like, well, we're in this very strange time right now where science is happening in real time and everything is being released as the discoveries are being made. And everyone is witnessing the scientific process in motion with adjustments, with fixes. And they, instead of saying, oh, that's how science works, they're like, oh, I can't trust science. They keep changing their minds. That's what science is. That's how it's supposed to work. It's not say one thing, prove it, and then it has to be true for all time. We have gone back even through the shape and analysis of the shape of the atom. We've gone through history and changed that from a round sphere to a mixed sphere to the atom with a nucleus and electrons on the outside to orbitals to electron clouds to, we learn more and we adjust our knowledge, and that's how science works. Nature of science is empirically based. It is comprised of theories and laws. It is socially and culturally embedded. It is socially negotiated, and it is inferential. And these are all important things. My intern made up this page, which is one of my favorite pages. And it's the difference between exploration and investigation. And we did this in a workshop for science fair, where we wanted the teachers to realize if you're doing science fair, you have to do an investigation. It has to be something that is testable. It has to be a true experiment. One of my personal pet peeves as a science educator is when someone goes on the Ellen show and says, I'm gonna do an experiment. I'm gonna mix these two things and watch what happened. And this cool thing happened. I'm like, that was a great demo, but it wasn't an experiment. You didn't test anything. There was no variable and control. And we've done this so many times that it's permeated into culture. And now anytime anybody does science publicly, it's an experiment. 101 experiments to do with your kids, and they're not really experiments. They're great demos or explorations, but they're not really experiments. That's my personal pet peeve. So here's a great page that talks about the similarities between exploration and investigation, and they are both important, and they are both science, and they are both hands-on, but they are not the same. They both rely on critical thinking skills. They both use a format of asking questions, but in exploration, you ask a question, you answer the question, and you may build a model to help you understand the question. In an investigation, you build an experiment, you find variables, you test them, you measure something, and you find an answer. And then you go back to your original hypothesis, you prove it or you disprove it, and then you refine your experiment, and if needed, and it usually is, you do it all over again. So they are different aspects of science. They're still both science. Now, I do like to focus on scientific investigations. So let's talk about the myth of the scientific method. And I'll tell you why in a second that I say that, but let's talk about what science is first. You ask a question. We always say that the scientific method starts with a question, something that we're curious about, something that makes us go, huh, I wonder why, and it's followed by something. I love this picture, the wandering rocks out in the American West. They find these rocks with these obvious trails that the rocks made, but there's no footprints. There's no water marks, no wave shape. What's moving these rocks? And it was a great mystery for a long time. Are they moving fast? Are they moving slowly? What are moving these rocks? So you see something, and then you can start investigating. Put down different types of rocks of different densities, put down different rocks in different weather settings. But what is making the rocks move? So you do research. You research these types of rocks. You research the type of sand. You research the weather. Is it a climate of high winds? Is it a climate of driving rains? Is it a hurricane area with lots of storms? You do your research to help you come up with a proper hypothesis. And when you develop your hypothesis, you do more than just make a guess. A proper hypothesis says, I think that blah, 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 because, and that word because is so important because it lets you know that, hey, I've thought about this and I have a reason for why I believe what I believe. It's not just a random guess. It's not a wild goose chase. I think this is going to happen because I did my research, and this makes me, so it's inferential. You've done research, you have an idea, and now you start developing your experiment. How are you going to test what you want to prove or what you want to know? Experimental design, one of my favorite things in science. How do I design a test that is fair and equal and lets me know what I'm looking for? So you design your tests, you get your procedures, you get your materials, you run your experiments. As the experiment is running, you start making observations. You take data, you take pictures. With students in your classroom, there's no reason for them not to take lots of pictures at home or in the classroom. We've got cameras almost everywhere we go now. There's no reason why we can't take lots of pictures. Excel will make data tables for you if you punch in a certain number and then hit a button and bam, all the graphs you could possibly want are made by the program. Keeping the journal is an important part. There are scientists who have tried to be defrauded because people didn't believe what they did, but because they had such thorough, and I got my science notebooks right here, because they have such thorough science notebooks and they can go back and say, hey, these are the steps that I did. Here's everything that I did. Here are the changes I made from my original procedures. Their experiments can be recreated, rerun, and then proven or disproven, but it's better than saying, oh, I didn't write down what I did. So keeping a journal is a major important part of science. At the end of that, you go back to your procedure. Do I need to restructure the experiment? Did I get good data? Does my data make sense? Why are there outliers? Are there outliers? Are those important parts of the data? You start looking at everything and thinking, do I need to run the experiment again, or am I good to go on to the next step? and then you present your explanation. Here's the data that I've collected. Here's what that data means. Here's why this is important. And then you go back to your very beginning and say, here's my conclusion. It proved my hypothesis was right, or it proved that my hypothesis was wrong. The point of the science isn't to prove the hypothesis. The point of the science is to find out what happens when, what happens if. So if your hypothesis was right, cool. If your hypothesis is wrong, cool. No one at a lab gets fired for getting a bunch of bad hypotheses. That doesn't happen that way. You don't get success rates at a lab. Okay, you run your experiments, and if it doesn't do what you want it to do, great, you learned something that didn't work. Try something else. The last step of the scientific method is probably the most important one, and it's one that we always forget to teach, and it is communicating what you've learned. All right? Jen is a researcher. She does a lot of research. I'm sure she's made some amazing discoveries, and if she doesn't know how to put that on paper or share that with somebody else, what's the point of doing it? If you don't find a better way to reach girls in STEM and then communicate to other people, here's what you need to do so that more girls are interested in STEM, what's the point of you doing all that work if you can't share that knowledge, if you can't get that into people's, their brains, into their work, into their readings? So finding out something is great, but sharing what is learned, preferably in a peer-reviewed journal, is the most important part that we don't talk about enough. Now, I called it a myth. And the reason I call it a myth is because I've seen this chart many, many times, where it starts with a question, you do background research, you construct a hypothesis, then you do a test, then you find out if your procedure is working. If not, you troubleshoot. If it is, you analyze data. You can come back here and go back to construct a hypothesis for some reason, I don't know why, or you can communicate results. And it's very linear-ish, and it's just not accurate. Looks more like this if you want to be honest about what science looks like. There is no real starting point. You can start with a hypothesis like, God, I wonder if I do so-and-so, if it'll make so-and-so work better. Great, that may not be based on an observation. It could just be an idea you have. Maybe you have a testable prediction that you want to know what happens. Maybe you think of an interesting question you want to know more about. Maybe there is an observation that you saw that gets you started on this process. Maybe you have a general theory from making observations that you want to test. It doesn't necessarily start with make an observation, form a question, make a hypothesis. It doesn't always start there. I've seen experiments going, and when the data starts to come in over here, gather data to test the predictions, and the data starts coming in, the data isn't what the scientists expected. And it was the coolest thing. It was in one of the cells at the magnet lab. The data came in, and the scientists looked at each other like, are you seeing what I'm seeing? Is this what we're seeing? And they immediately in sync started adjusting and changing the experiment because they were onto something, and they needed to change what they were doing because they realized that their original idea wasn't what they wanted to do. So they started here with gathering data and then went back to refining their hypotheses. And at this point, I'm sure the hypothesis, you don't stop to write down the hypothesis. There's so much into the process of science that they're like, oh, okay, we've got an idea, and they just run with it. And they went right then and started here to here to here, and then start going around. So science doesn't necessarily follow a straight line. It's great for children to see something like this and realize, okay, these are the general ideas, but in actuality, it is a mess of directions, and all these arrows can go back and forth into each other too. All right. Martin and Stephanie, I'm going to ask you to come at least unmute yourselves because we're doing a group activity, and we're going to talk about observations versus inferences. Now, first I'm going to explain what observations and inferences are in my world. And in my world, observations are the active acquisitions of getting information, using your 5 senses to get information as you do science. I always tell students that an observation is something that is factual. I'm wearing a purple shirt. I have glasses on. There's a headset on me. These are things that are factual that you all can observe and verify. So these are observations. Now, an inference is something that's a little bit different. An inference is an idea. It's something that I think, but I'm not sure about. For instance, if I show you my mug, you can see my Wakanda Forever mug that I've got here. That's an observation. It may give you a clue as to who I am as an individual, where I like to spend my extra money, where my fandom is. I love using that word. So an inference is something that you don't know, but you get an observation and it gets you thinking some way. So if I show you this mug, anybody want to make an inference into what I like?
Comic books.
Okay. I do have a pile of comic books off to my side next to me, so that is a good inference. Anybody else?
It's hard to see you.
Okay. So I've got my Wakanda Forever mug here. I'll put it right in front of me. There you go.
Like coffee.
All right, that's another one.
You like drinking things.
Good. Stay hydrated. So I could be a mug collector. I could be a drinker of coffee. I could live with someone who is a Black Panther fan or a comic book fan or a Marvel fan. Jen knows me enough and she's seen my office enough to know that Marvel comic books are not my true love. My true love, let me see if I can reach over here and grab him. Oh, here he is. No, that's that one. This is him. All right, here he is. Ladies and gentlemen, this is Starscream. He's a Transformer. He's a bad guy. He turns into an airplane. And this is my favorite character of anything, anywhere, ever. I'm a Transformer guy, all the way through and through. Jen's laughing at me because she's in my office. I have too many toys in my office.
Yes.
I have almost every toy in my office, but you don't see that right now. You only saw that one piece of information. So that is a thing. That does not make your inference bad because your inference was based off the observation that you did have this. So the act of observing is important. The act of inferring is important, but the inference does not necessarily have to be true like the observation does. Your observation is, what do you know? I'm wearing glasses. How do you know it? You can observe that I'm wearing glasses. What does that tell you about my eyesight? What do you think? Not 20/20 anymore. Right. Why do you think that? Because wearing glasses is something that is used to correct someone's vision. So you have your observation, you have your inferences. Now, am I wearing glasses because my eyesight is bad, or am I wearing glasses because I read an article that says that people seeing other people with glasses makes them think that those people are more intelligent? I'm not telling you. But that is another possible reason for why I'm wearing glasses. Maybe I think I look better with glasses, so maybe that's why I wear them. Maybe they're one of those Hollywood fake glasses. You can see that there's actual lenses in there, there's reflection, but are they prescription lenses? You don't know. And until you test that, it's an inference. Until you know for sure, you don't know. When I take these off, actually I need to go, doctor. My looking across the room is more in focus, but looking down here, I can't see the names anymore. And now I can. So there's your answer. Science joke time. 3 people are traveling by train through Scotland. In fact, they just entered into Scotland. They just passed the border. When they see a black sheep through the window of the train, and the first person goes, I see all Scottish sheep are black. Second person goes, nah, some Scottish sheep are black. The third person is the scientist who's well-versed in observation and inference. And the third person, the scientist, says, there is at least one sheep in Scotland, and at least one side of that one sheep is black. I love this joke because that's how scientists have to think. You can't assume something during your experiment. Until you have evidence that something is happening or not happening, you can't assume it, or else your entire experiment goes off. One of the things that my professors in college said, make sure that you're not fooling yourself when you're doing the science. Okay. Participation time. I've got a thing written on the screen that is being blocked by a light purple bar. Can anybody read this?
My something something.
All right. Let's see, we got something in the chat. What's it say? Okay, let me show you a little bit more of this and see if I can't help you read this a little bit better. Anyone?
My cup of tea.
Okay. Do you know that or do you think that?
I'm inferring that
Excellent. How come you're inferring that?
based on what I'm observing.
Okay. How's that look?
Looks like I'm starting to feel less confident.
Now see, this is tricky because in science, the more you get to see, the more confident you're supposed to be in your theory, your idea, your hypothesis. So let me show you a little bit more about my cup of tea, which we are less confident about. Anybody want to try and read this? I like doing this in the classroom, and I'll tell the kids, if somebody can tell me what this says on the very first slide. On the very first slide, and you get it right, I'll give you 100%. I'll talk to your teacher, make sure you don't have to do any work for the rest of the day. But if you get it wrong, you get an F for the day. Yeah, they all say my cup of tea. And then here they're like, oh, it's mixture of tea. I'm like, oh, okay, let's keep looking at this. And the more I show you, the less confident you are because I am tricking you. So let me show you this. And let me ask right now, are you confident in what this says right now?
Yes.
No,
Why not?
because you're a tricker.
But I've shown you the whole thing, right?
I don't think you have. I think you've shown us something, but there's more to it. There might be more underneath.
Like this?
Oh.
See, then that's just it. Until you see 100% of the question, you don't know. And in science, our job is to try and see 100% of the question. And it could be increasing magnet strength, or making microscopes better, or making lasers hotter, or more refined, or more focused. Whatever it is that we're doing in science, we're doing to get more information to see something better. That's why we do what we do. And you got to remember not to be fooled by what you're doing. Don't believe everything you read on the internet just because there's a picture with a quote next to it. Abraham Lincoln said that, and he was the 16th president of the USA. Obviously, right? Yes. So what is science? And this is truthfully participation time because I'm going to ask you the question. I'm going to sit back and let you all talk about what you think about what I said. So science can solve any problem or answer any question. Is that science true or false?
I'm going with false
Why?
because it can't solve any question. There are some questions that we won't be able to solve.
Like what?
Questions about the spiritual world, perhaps.
What is the meaning of life? Science will never be able to tell us what is the meaning of life. There have been scientists that have tried to weigh, quantify, measure a soul. That's not something that science can do. They can try to prove a soul, but until now, that's not something science can do. Science cannot tell you, what should I have for dinner tomorrow? Science cannot tell you, am I happy at my job? There are things beyond what science can answer. So yes, we do science to try and make our lives better and answer questions, but there are questions that are outside the realm of science. That is why philosophy exists. That is why religion exists. There are other fields out there that are beyond science. Science is concerned with understanding how the natural world works. True or false? I get a true from Jen. Stephanie Ibrahim? So the big idea of what science is does fall into this. It is something that we're trying to understand. It's something that we're trying to explore. But we do science to ask questions about the observable world around us. So that is where our wheelhouse is. That's where we're focused on. Science requires a lot of creative energy. What do you think? It's a tricky one. The dog likes it. The connection between creativity and science often gets overlooked because they're like, no, science is very black and white and data and you do your data and you do what the data tells you. But trying to understand what the data tells you is important. We have run experiments at the Magnet Lab that have left us confused, more confused than we were before we ran the experiment. And the director of the lab, Greg, likes to say that either we're asking the wrong question, we're testing the wrong thing, we don't understand the data, or Mother Nature just has a quirky sense of humor. And it's one of those things that we can run this great experiment and get all this great data, and if we don't know how to interpret that data, it's meaningless. So creativity is important, from being able to go from, hey, this is the way, this is the model that we have, to, hey, this new model fits the new data better. And it is a youth movement, because some of us have been in science for so long that we've been indoctrinated to, this is how it works. This is how that model works. And then these new students come in and say, well, why don't we try this instead? Scientific revolution is another interesting thing. And it's one of those things that getting out from what we know is another tricky thing. So yes, creativity is important. Scientific hypothesis is just an educated guess about anything. True or false? So this one's going to be false, because a hypothesis is more than just a guess. I mentioned that earlier. It is backed by research. It is backed by inferential and observations. It is something that is not just a wild guess. For instance, looking at your teacher and thinking about how old she is, that's not a hypothesis. All right, that is just a guess. But actually going in and finding out when they graduated from school and how long they've been teaching, and now you start getting data, and now that becomes a hypothesis. So it's not just a guess. Science is more concerned with collecting facts. No. Is it part of science? Absolutely. Facts are very important. Data is very important to the process of science. But is it concerned with collecting facts? Not really. It's a lot more than just that. A scientific fact is absolute, fixed, and permanent. True or false?
False.
You remember the Brontosaurus? There is no such thing as a Brontosaurus. You can go to most adults now and say, remember the Brontosaurus? They're like, oh yeah, it's a long-necked dinosaur with a long tail, and I'll be, no, that's a brachiosaur, or a diplodocus, or a patasaur, or any ultrasaur, any one of the long list of the family of the long-necked, long-tailed dinosaurs. Brontosaurus was supposed to be one of those, but in the early days of paleontology, when scientists were discovering all these new bones and putting together new skeletons, they put the wrong animal head on the wrong animal body, and they called it a Brontosaurus. And after about 60 years of exploring, somebody goes, how come we've never found another one of these? Upon further review, that's the wrong head on the wrong body. That's not a real dinosaur. And it's one of those things that we rushed and we got it wrong, and that happens.
You just made me a little sad, Carlos. I didn't know that.
I told a friend of mine how rainbows actually work, and he goes, you just ruined the magic of rainbows for me. So I am a ruiner of magic sometimes. How about this? Scientific theory is merely a guess. Again, I will tell you this, there is a paleontologist out there that says that the next long-necked dinosaur that they discover, they are going to name Brontosaurus, so that we still have that on this earth.
I hope so. I hope so.
So is a theory merely a guess? theory of gravity, theory of plate tectonics, theory of evolution. Are these just guesses? A theory is a well thought out, heavily proved with lots of data behind it, explanation for how something works. Now, a theory is not a law. And the reason is because a theory is an explanation and a law is an observation. If I take a balloon and I squeeze the balloon, the pressure inside that balloon is going to go up. That's a scientific law. Every time you squeeze a balloon, that pressure is going to go up every single time. Plate tectonics, when two plates collide, they don't always work the same way. They can work a variety of different ways and even new ways that we haven't discovered yet. So that is a theory. Evolution can work several different ways. It is a theory. But if you take a balloon and increase the temperature inside that balloon, the pressure is going to go up. And that is an observable thing, and it's going to happen every time. So those are theories. The other two I use are laws. They are different things. Theories do not graduate into laws. That is not how science works. Scientists have solved most of the major mysteries of nature. True or false?
False.
I love this question because every time we make a discovery, 3 or 4 more questions come out of that. And I will tell you one that we discovered very recently that I don't think you know. But if you've ever seen an Arctic fox, Arctic foxes go in the snow and they dig around and they smell, and then they'll pounce where they think they found their prey, and they'll collapse that little nook or cave or whatever it is, and they'll dig in there and they'll catch their prey. We believe these foxes can see magnetic field lines, and we think this because when they're hunting, they pounce northwesternly. In fact, 20 degrees off from magnetic north. And if they pounce northwesterly, they succeed in capturing prey 80% of the time. If they pounce from any other direction, that success rate drops to about 18%. Why? We discovered something. It gave us 4 more mysteries. How do foxes see the magnetic field lines? Why are they hunting, or why do they pounce from a northwest direction? Why do the other directions not work? Why northwest of all directions? It's one of those things. And Jen, you have a dog, I heard it, right? Next time you take the dog outside to go to the bathroom, I'm willing to put money that the dog poops north-south.
I will let you know how that turns out.
Because that is another observable thing that we have done in this world. Dogs tend to poop north-south and will only poop another direction if they are forced to. Yes, somebody did this research and that's what they found out. So why? That's what I'm talking about. We solve one thing, more mysteries come out of it. So science can be influenced by the race, gender, nationality, or religion of the scientist. True or false? I would like to think that science is clear-cut and free of any outside influences, but it's just not true. And I'll give you an example in engineering. When we started to discover seatbelts as a good thing for consumers and drivers, we tested them by using crash test dummies, and the engineers designed the crash test dummies. They put them on the seat, they tested the person, they crashed the car, and then they found out how it worked to save lives. And for a while after seatbelts were put into cars, it saved a lot of men's lives, but not children and not women, because they have different body types. And all the male engineers failed to realize that there are different body types out there for women and children, and they just blatantly overlooked something that a woman engineer would have brought up. The gender was an issue there. A lot of cameras have face recognition software now, and that works great for identifying white men, but not Asian men, because the eyes are harder for the software to pick up. It also, my camera, I love my camera phone, it's got night vision on it, which is very cool, and it can find faces in night vision. except for African-American faces that are a little bit harder to pick up in dark. So all these little things that we don't think about are things. And I'll give you one more that absolutely drives me crazy. My kids have become major gamers. They like playing video games. And most of the heroes in a lot of video games they play are white men. And yes, there are some video games that have women in them, and that's great. There are not a lot that have African-American heroes, and there are hardly any that have a Hispanic hero. So these are the struggles that I have. I want my children to see a Hispanic hero killing aliens and saving the world, but I've never seen that before. So it matters. Representation does matter. Disagreements between scientists show the weakness of science. True or false? Disagreements between science shows the strength of science. All right, when scientists disagree and they argue, and I love seeing scientists argue, they rely on data, they rely on facts, they rely on observations, they do not rely on name calling, they do not rely on bullying, they do not rely on a lot of things that politicians do. They actually look for the data and they argue with the data, and quite often they come up with a new model that helps to align both of the data sets, or they find faults in the data set and go, well, your data's wrong because you're using an outdated instrument, or no, you didn't reach the right temperature to run the experiment at, or all these things that they argue over, well, your experiment didn't work because so-and-so. This is a strength of science, not an actual weakness. All right, I'm going to let Jennifer take over for a second and talk about the Virtual Science Collaborative and additional resources that are on the website. So Jen, this is all you.
Thank you. So the Virtual Collaborative Science Collaborative is sort of the organization that we put together to provide support for teachers during these uncertain and ever-changing times, when teachers are trying to teach kids in blended spaces. And so the workshops that we're putting on, which Carlos is doing the Nature of Science, and we're having another one by Sherry Sutherland in 2 weeks about the nature of science. And Carlos has done one previously on magnetism, which was full of great content knowledge. I learned a lot.
Glad I got to go before Sherry, by the way.
And so if you're interested in nature of science, Sherry is sort of an expert. She's written a lot of, done a lot of research on nature of science and written a lot of books on nature of science. So
she wrote the book on nature of science.
Yeah, so she'll be a great resource if you want to attend that workshop. The reason why we chose nature of science is because of the county that we're actually in Tallahassee, Leon County. This was a subject that the teachers wanted to have covered in this first part of the year, because this is something that often teachers cover in the first part of the year. So we have the workshops, and we're trying to sort of target areas that teachers need or want covered. In addition, we have, we're recording these workshops and we put them up as video resources, and we have some other resources that people that are part of the collaborative have provided, giving information about virtual settings and how to really utilize the tools in those settings. And then additionally, the materials that we have. So we're curating a resource with particular lessons that work well for blended spaces, that really support learners across these different ways that they have to learn. So we're constantly adding materials here. We have updated a couple of those resources with sort of more traditional nature of science labs that are done in person so that they can be done in blended spaces. And then we have a couple of teachers who have recently done some longer lessons on nature of science, looking at that in terms of Snook and sort of marine science settings. So we have those up there, and those are for blended spaces where students are in both person and in Zoom or in virtual settings. So all in all of our resources are free, but we're really just trying to support teachers. And so if you know teachers, or you know anyone in particular that has a need that needs us to work on it, we hope that you'll reach out, or that you'll be part of the collaborative.
Awesome. Another resource for everyone to use is the Magnet Lab website, because we now offer virtual classroom visits. So I can come in through Zoom with the same background, the same setup into your classroom and talk with your kids about magnetism, electricity, electromagnetism, or the magnet lab itself. And these are the 4 options that we're offering right now. Free to all teachers. All you got to do is go on the website, submit the request form, go to the calendar page, request a date, and bam, you're in. We will confirm that to make sure it fits. You can also go to the Magnet Lab website and go to Magnet Academy, which has a number of cool things, including if you go to here to plan a lesson, I've written the lesson plan for you. You can copy it and paste it and have it ready for your administration, your principal, and they're all aligned with the Next Generation Science Standards from the National Science Foundation and NSTA. So you can go here, explore history, try this at home, a bunch of fun activities, demos, learn the basics, and we have some tutorials. You can play online with some electromagnets too. So lots of fun stuff you can do with the website.
Can I ask you one question? So
yes.
the previous slide talks about the materials. So you ship out classroom kits for your presentations?
So this is a screen grab from our website, and we have classroom kits that are available for teachers to pick up. However, with COVID going on right now, that's just that program is suspended until things get better.
Oh, okay. So, sorry, I didn't.
Yeah. No, it is a dream to have those kits and send them off across the country. I'm not sure we want to spread those germs like that right now. I have seen kids put these magnets in their mouths and nose and everywhere else because kindergartners get some of these kits. So one day we'll be able to ship them nationwide, but as of right now, this is what we've got. So, all right, I'm going to stop screen sharing and bring everyone back here. Stephanie Abraham, did you have any questions?
Yeah. I don't. Thank you so much. It was very interesting.
I'm glad you got some cool stuff, some ideas. Hopefully some things you can do in your classroom. And this is Skylinks. This is my new one that I've got. But you can't guess what it turns into.
I bet you I can. Oh no.
It's a space shuttle, see? Okay, that's my toy for today. Abraham, are you good? All right, Jen, I think we're all done.
And we'll post this video, so if you wanted to share it with other teachers that weren't able to come, I know some teachers are interested. We'll put it up on our website and share it.
And it's free for everybody to access too, so.
Thank you, Carlos. Thank you, Stephanie Abram.
All right, thanks everybody, and I hope to see you in January. I will be doing Step Up Physics, and definitely go see Sherry Sutherland. Like I said, I don't exaggerate. She wrote the book. Her textbook. Her book is the textbook in her course, and rightfully so. So, all right, thanks, Jen.